Welcome everyone, and thanks for taking time to attend this seminar. Today we will highlight some of the tools that MSC has to offer in the area of optimization for you to stay competitive in the marketplace. Irrespective of the design, irrespective of the industry that you're in, one will try to stay ahead of the competition by continuous improvement of your design. And by this improvement, we mean reduce cost and improve performance. Generally, cost reduction involves making good decision early, reducing the weight of a component by selecting appropriate material, doing proper sizing, and the performance generally means meeting the specification required for the design. And often the risk identification means you want to be able to find out what variables are going to affect your cost as well as your responses of your design. So you want to be able to find all of that information, and Nastran can help you with that. The challenges are generally associated due to, just 1 second, I need to advance the slide here. Okay. Today's design environment is multidisciplinary, so you're involved with static, buckling, dynamic response type of requirements where you might have, for example, your frequency needs to be higher than specific frequency. For example, in this case, I'm mentioning 50 hertz. You might have some random response requirements so that your RMS values are not higher than a certain stress value. Stability criteria, for example, would involve the complex eigenvalue solutions. You may have requirement for stability, and you may also have requirement for acoustic in the interior of a car or an airplane, for example. And if you're doing aeroelastic analysis or aircraft design, then you might have some aeroelastic response requirement and the flutter requirements. So you're trying to modify your design and you're trying to meet all these different requirements. And to change your design while meeting all these requirements is a challenge. And oftentimes you go back to your experience level, do trial and error or build and test, but all of these methods are highly inefficient and does not produce sure results. So what you rely on is generally the stochastic method, gradient-based method, or the design of experiment type of analysis is to be able to give you a design that meets all of these different multitudes of requirements. And Nastran optimization can help you with that, where you can, it's a multidisciplinary optimization so that you can have a run that has all of these different analysis set up within one input file, and you can try to simultaneously meet all of these requirements and often conflicting requirements, and you can optimize and come up with a design that satisfies all of these different criteria. Okay. Optimization methods available in Nastran are sizing optimization. Fully stressed design is supported for sizing optimization. Shape optimization has been around since version 68. Topology optimization has been around for a while. In the recent years, we have added topography and topometry optimization, along with automated external superelement optimization, which can end up reducing your optimization runtime quite a lot. And then we have a multi-opt capability to be able to optimize different models, topological models simultaneously. You might have a model for acoustic, and you might have model for static stress analysis, and you can optimize these different models simultaneously. Then we have a nonlinear response optimization also allowed, where you can have contact in your optimization run. Material or geometric nonlinearities can be supported through that functionality. And all of these processes allow you to calculate external responses, meaning you can write a user-written program that would use values calculated by Nastran and formulate your own responses from an external routine, and you can control that. And that could be a cost function or some other elaborate margin calculations or things like that. So let's go ahead and go look through this optimization and what it involves. Basically, it's in optimization problem, you're trying to define what variables you are allowed to change and by how much, and what responses you are interested in monitoring, and what should be the values of those responses. If your current design goes above the allowable values, optimization will try to bring that in within the bounds, while meeting design objective, which may be your minimization of your weight or some RMS stress value. So that's basically the optimization problem statement that you're trying to define when you do optimization. And that's always multidisciplinary. So you can have a static constraint as well as modal buckling or frequency response type of constraint in the same run. Here is a schematic of the design optimization process, and the key strength of the MSC's approach is this approximate model here. Approximate model is basically calculated based on Taylor series approximation and the sensitivities. For each optimization job, sensitivities are automatically calculated. That's basically a matrix of information that tells you how the responses are affected by a design variable. Okay. And what Optimizer does is it communicates with that approximate model every time that gradient information is needed to move the design forward. And once the new design variables are found, you go through and do structural analysis again and calculate the sensitivities. What approximate model allows you to do is minimize that complete design, complete analysis many times. So the amount of time you have to run a complete analysis is reduced as a result of this approximate model concept. For sizing optimization, you can have different objectives. It has to be a scalar quantities, though. So if you're going to combine two different responses, you have to combine two different responses to formulate a single response if you're going to use the multiple objective type of scenario. So you have to formulate a what we call a type 2 response to be able to do that. And so one thing to remember is that design objective has to be a scalar function. Then we define a design variables. It could be ply thicknesses, could be material properties, ply orientation, also the location, in some cases location or orientation of your cross-section could be used as a design variable also. So anything that's on your connectivity entry can be used as a design variable as well. And the design constraints can be specified in the sizing optimization, and the complete list of these constraints that are permitted can be found in the quick reference guide under the DERESP1 entry description. When you do the sizing optimization, optimizer generally is varying these design variables in a continuous fashion, right? But oftentimes these components cannot be found in those the sizes that Nastran optimizer may come up with. So you may have a need to select from a discrete value of your discrete values of your design variables, so that you can only get components that are readily available in the market. For example, certain size beams with certain cross-section, flange height, width, and thicknesses, etc. And for doing discrete sizing, Nastran allows 4 different options where we round up or round up to nearest design variable, and then there is a conservative discrete design and design of experiment. Those are 4 different methods available. So after the continuous optimization or mathematical programming approach is completed, Nastran would run the optimization using these discrete values and make sure that your constraint was satisfied. If not, it will report it as such and give you the final results. So the discrete sizing is supported in Nastran. The other option that is allowed in Nastran is the shape optimization. Here we are showing you an example of culvert type of structure where we are trying to reduce the volume while meeting the stress criteria. And what we are trying to do here is we're trying to keep the outer profile of this shape the same while changing the circular arch. We want to be able to change the circular arch to reduce the volume and therefore the weight while meeting the stress criteria. And here in the shape optimization, the design variables you use are the grid movements. So you have to specify grid movements which can be combined into your final shape. So this particular run, what we did was we extracted displacement patterns by applying loads at these interior grids. There are 7 locations where we applied a unit load to get the displacement pattern, and those combination of the displacement pattern act as the shape basis vector to give you the final design. So you can see that here the volume was reduced by more than 20%, and the stress constraints was met. Okay. Same thing here this is other example here where we have a cantilever beam where we want to be able to modify the shape of it so that the volume or the weight is reduced while meeting the stress criteria. We have a tip loading here, and in this example, we allowed only the top and bottom surface to move. So we provided the shapes for the top and bottom surfaces by applying unit loads to it and creating the shape factors. That resulted in this shape that you see on the right-hand side with a volume that was reduced by more than 33%. So your shape optimization results will very much depend on the shapes you put in, and these are called shape basis vector, and there are 4 different methods allowed for the shape basis vector. You can do manual grid variation, direct input of shapes, geometric boundary shapes, and analytical boundary shapes. These are in detail documented in the the Design Sensitivity and Optimization User's Guide. The next is the topology optimization. It's topology optimization, topometry optimization. Topometry optimization is a special form of size optimization where each element is designed. And so each element thickness acts as a design variable in a sense, and you can get a material distribution through your component, and a very large model can be analyzed using this technology, this method. You can see the whole car model was analyzed to give you a thickness distribution that would meet certain criteria. The contour below basically shows the thickness changes it goes through, a component may go through the design process. And it allows, or it comes up with a design with a continuously varying thickness, basically element by element. Okay. So it gives you a good idea of your material distribution to meet your design requirements. You can do that for ply thicknesses as well in a composite analysis, and here's an example of that. The other form of optimization that is available in Nastran is the topography optimization, where it's a special form of shape optimization where component that is initially flat like this, you permit it to move, permit certain elements to move up normal to the surface, and cause the shape change to come up with appropriate to meet your constraints and objective. And this type of methods are also known as the bead or stamp optimization. Okay. All the disciplines are supported under here: static, normal modes, buckling, complex eigenvalue, and frequency response solutions can be used for this type of optimization. Here is an example of a panel on a spacecraft structure, and this was optimized to keep with the weight minimization criteria while keeping the frequency above a certain value. And you can see the complicated, intricate shape that it came up with to meet that. It would be hard to come up with a design like that manually. One other optimization process that is available in Nastran is topology optimization process, where you start up with a very crude representation of what you think may meet the requirements. So you basically have connection points and a big block of metal, essentially, to start with, a finite element model of that with appropriate loading and boundary conditions. And then you use the topology optimization to bring the weight within certain, cause basically a weight reduction while minimizing the compliance. Okay. So here you come up with this shape, and then you have to go through the smoothing process and sizing optimization to finally get a part that is optimized. So it gives you a good idea of your. It gives you a good idea of what your final design may look like, and gives you a starting point for your design. So once you have this, you can refine it, take it back into CAD after smoothing, and do some final designing. Here are some other examples of this topology optimization, where you start with a very crude design and loads and boundary condition, and you can see how this clip was designed, clip configuration was produced as a result of topology optimization. And a great amount of mass savings can be achieved using this technique. Here is another example that everyone may be familiar with, is that your bike frame structure for two loading conditions. Here we have loads applied at the handlebar, seat, and the pedal, and then we have a load applied at the handlebar and the pedal. And for this design, it comes up with some logical-looking design that most bike frame adhere to. So that basically proved kind of like a proof of concept for loading and the design that people have been working with over the years. Another options that we have available in Nastran is the manufacturing constraint, because all the design that topology may come up with may not be manufacturable. So you have to allow for manufacturing constraints. So in this example, we have added the extrusion constraints so that you can see that this component will be extrudable. Whereas one on the right, we added a different type of constraints where we had a symmetry about the YZ axis and a casting constraint along the Y direction. So depending on the manufacturing constraints you have on your parts, you can come up with a different design, and it can help you along that task also. So if your parts can only be manufactured by extrusion, then you would want to use this design. But if you are going to cast your part, then you probably would want to use this design. One other method allowed in Nastran is called automatic external superelement optimization, AESO, and that builds up on our superelement technology, where non-design model is reduced, statically or dynamically reduced, and a component mode reduction process is used. But the user doesn't have to be familiar with that at all to be able to use this functionality, because what Nastran would do is put in all the non-design component in the external superelement and reduce that and keep the design components into residual to be solved for. So you can use this for efficiency improvement, especially if you're designing a small portion in a large assembly of structure. If you're only trying to optimize a small portion within the large assembly, you can definitely make use of this and take advantage of it. Okay. Here is an example, AESO example, where we had a 1.4 million degree of freedom model car body, and if you're going to use optimize this, you don't have to carry all of the engine along. You only carry along the parts that are designed and the responses that you're trying to monitor into a design model. And you can do that with AESO, and you can see that the runtime for the full model versus the AESO model was 1/4. So the AESO model clearly can save you a lot of time, the runtime. Other method that is in Nastran is the multi-model optimization. Multi-model optimization allows you to optimize on up to 5 different topological models. So you can have one model that is created for stress analysis, and the other one may be created for acoustics or some other purpose or a crash, and you can optimize all of those 3 models simultaneously. So each of these are separate input files, and Nastran would do is, based on your design variables and such, combine this multitude of models of 5 different models, up to 5 different models, into a single model create do a sensitivity analysis and do the optimization task. So all of those models can be optimized simultaneously. Okay. And the advantage is simpler to use. There is no DMAP required. Each one of the analysis can be run in parallel. It's called blocked or unblocked mode, using different memory requests for each one of the analyses. Also, the discrete optimization is supported through this functionality. You can also combine, in the multi-model optimization, you can combine objective from the different analysis and formulate a single objective function, which you can try to minimize. Okay. So one of the application might be if you have a same wing structure with two different fuselage configurations, you can use that to optimize both designs simultaneously. Here is an example that was done for the acoustic model, stress model, and stress response model, and some with the displacement constraints. So you can see that the model are completely different. This has a lower mesh density, this has a higher mesh density, and this here is acoustic model. You can do optimization on all three models simultaneously, although the input files are all distinct. The user doesn't have to worry about combining them and such. Okay. So in that particular design, your weight was reduced from 643 to 573. And you can see how the design variables change during the design iteration process or design optimization process while meeting your constraints. So first, your constraints were violated, and then constraints were brought within the bounds for the final designs. One other optimization feature that has been recently added in Nastran is the nonlinear optimization feature, where you're allowed to have a material and geometric nonlinearity. This is based on the equivalent static load concept, so you are able to solve problems with the contact definition, material and geometric nonlinearity. Size, shape, and topology variables are allowed in that case, this is supported by solution 400, not by solution 200, as like all the other optimization features. So in a nonlinear optimization, you go through a nonlinear load increment, and for each increment, you will go through a design cycle until all of the load is applied. This is basically the summary of using Nastran optimization feature, is that you can combine shape, size, and topology optimization in one run. You're allowed for a parallel sensitivity calculation. That feature is available. You can have multiple mass targets for topology along with manufacturing constraints. Topography and topometry optimization can be used as well. That allows you to get a better mass distribution or the topography information to satisfy your design. You can use it also for analysis test correlation type of studies. So you can try to match your analysis model so that the test and analysis model correlate. You're allowed the functionality exists to put in external responses or through your Fortran routine for example, to calculate cost functions or margin of safety type calculations. So you can evaluate how a specific design change will translate into a cost, how much it will affect the cost. So you can put in those elaborate functions to do that. Discrete design parameters are allowed. The performance of these runs is fairly fast and improved tremendously in the last few years based on the iterative solver and the DMP technology that is supported through Solution 200. It's continuously being improved and enhanced, and there is significant pre- and post-processing support via PATRAN. You can also get help for this optimization capability through our support line and through Sim Companion knowledge base. There is a webinar that goes through and shows you a start to finish process in PATRAN, so you can look through that as well. And what I will do is now show you the PATRAN GUI, and I hope as a result of this webinar you are exposed to a different capability that you may not have been familiar with earlier, and will be able to use this in the future and provide us feedback as you start using this. So let's go ahead and look at the PATRAN GUI. And I'll bring up this model here in PATRAN version 2012 and show you different aspects of it and where you can go to create this type of input for this optimization capability in Nastran. So if you go to Analysis menu, there is Analyze and Optimize options. So if you go to Optimize, it can do size optimization, and topography, topology, and topometry optimization can be done through top optimized menus here. Okay, and if you go optimization parameter or translation parameters, actually objective and constraints. Here is what you have: topography, topology, and topometry optimization is supported through top optimized. For sizing optimization, you can go to Optimize and then go to Tools, Design Study, and Pre-Process. That will allow you to create your design variables. For example, here in this particular model, I have each one of the element is a design variable. Each element thickness is a design variable, and you can see that they're all listed there. You can create your responses, objective constraints, and so on. And you can and when you're done, you can look at the summary of your design study, which will list, for example, all of your design variables, your constraints, and so on, in your objectives. So you can see your design task that you're undertaking. Okay, and once the analysis is done and you bring in the results, you can also view your plots for how the design variables changed and how the constraints are changing as a result of your optimization process. So here is a plot of design variables, and the reason why you only see 4 curves here, although you have a whole bunch of design variables, is because these 4 variables were linked to all the rest of them. So the control was in place to be able to change the thicknesses of the element in a row. So each row of element here will be kept at a certain thickness. Okay, so these first four elements were used as controlling variables, and all the rest of them were linked to that first four variables. Okay, and so that's why you see that in this particular graph, because all the other variables are based on the first four. Now you can also look at how your constraints change, and you can see the change in constraint as the design progressed. And one thing to keep in mind that this is not just one constraint. You could have several constraints in your model. This point could be referring to your displacement constraint, while this could be referring to your stress constraint. But this is basically telling you that maximum constraint is a normalized value of constraint and how it changed over the design cycles. And then you can look at the objective function, which could be weight in this case, as to how your objective function changed. Okay. And so all of these capabilities are supported. For topology optimization, you can also do smoothing that's allowed under design study post-process. You can create a FAM smooth option once you do the topology optimization. So smoothing options are also allowed through Patron, or functionality is also allowed through Patron. And for any further information, I will refer you to Design Sensitivity and Optimization User's Guide if you're interested, and you can send in a question or comment, and I'll try to respond to you. I think we can open it up for, that's all I have for today. We can open this up for question and answers.